Good afternoon, ladies and gentlemen. Welcome to the next Jerzy Pniewski colloquium of Institute of Experimental Physics. Can you hear me? Okay. First of all, I thank you that you are not scared by the bomb alarm. And we were afraid that the room will be empty, but you came, so thank you very much. Second, before I introduce our speaker, I want to make an announcement. As you know, at this faculty we have two colloquia, one organized by experimenters. This one, oops, did it finish or? Two? Oh, okay, dobra. My hand is blocking the radio waves, funny. So, so there are two colloquia, different. One is theoretical, Leopold Infeld, another one is experimental, Jerzy Pniewski. And the directors of both institutes agreed to join two colloquia, and we will have one common faculty physics colloquium starting from the next academic year. And one consequence is that we will make sure that there will be no teaching hours during this time, so all students and all teachers will be able to participate. Second is that the students and PhD students will be able to sign up to this and get some ECT points for that. So we are looking forward to have a common colloquium with more people attending. Okay, and now let me welcome our guest, Peter Thirolf from Ludwig Maximilian University in Munich. Peter graduated from Heidelberg. He made a PhD in Heidelberg. Later he was abroad in NSCL, I found in his CV, where many of us do experiments, and finally he settled in Munich. He is active in different branches of physics. For example, he is very well known for the development of laser-driven acceleration of ions. This is a very interesting project and the rising technology of many new applications. However, we invited him today not to talk about laser accelerators, but for a different topic in which he made himself famous already. I dare to say that. The issue of thorium-229 isomer, which is very, very interesting piece of physics, which is actually joining or combining nuclear physics, atomic physics, optics, quantum physics, many different things. So he will tell us today about this part, because he managed to make a very important breakthrough recently in this field. I want to remind you that we in Warsaw were also at some point interested in thorium-229. Jan Żylic came up with a very nice idea of spin mixing oscillations, and this idea was worked up by him together with Professor Wycech and Professor Pachucki. But in 2005, Jan Żylic was awarded the Smoluchowski Medal for this work, which is the highest distinction of Polish Physical Society. So we are very interested in this topic. We just put our fingers in it a little bit. I mean, Jan mainly. Okay, so let us invite Peter, and I give the floor is yours. Tell us the story, please.
Thank you, Marek, for the kind introduction, for the invitation to be here. It's a pleasure to be here. I'm grateful that you, in such a large number, came here, despite the unfavorable external, situation. As I came here, I heard the sirens alarm and everything. I thought, well, what will happen? So I'm glad that you're here, and that I'm glad that I can tell you now about what we are doing on the way towards a nuclear clock. So we are talking about time measurement, physical time measurement, and that spans from, what I wanted to tell is that the story now goes about physical time measurement, and you see from the left and switching in a zigzag mode that this spans 5,000 years of technology, let's call it, starting from the first sundial clocks. Then in the medieval times, time was measured in a way that in the monasteries they took candles, and a candle took, let's say, 10 times an Ave Maria or something like that, and then the burn down of the candle was a measurement of the time. Then you all know about the sand. Then came the mechanical clocks in different qualities, increasingly over time, until then comes the digital age, the quartz clock. And then what should come now, and which is not here, is the state of the art, which we will hopefully then see soon, the atomic lattice clocks, which is, well, atomic clocks are the state of the art at the moment. Single atoms or a whole ensemble of ions, either in a trap or in an optical lattice done by, well, laser fields. And they have, at the moment, already orders of magnitude improvement on what is still the standard of time measurement, or the definition of the time based on a microwave clock on cesium. But what we are now looking into is there a possibility to overcome and to surpass and to outperform the performance of optical clocks, even in their best modality, by something like a nuclear clock. And the thorium isomer is the only in the whole landscape of nuclear states possibility where a nuclear state qualifies as a frequency standard, as a transition that goes in the direction of being ultra precise. Can I put that? And this, at the moment, this here is the atomic lattice clock, where you have atoms sitting in this laser field, like in a cage by optical, by optical forces. And the question is now, and this brings me to the outline, would thorium-229, this actinide nucleus, have the properties for a nuclear clock? So I will tell you a little bit about, as an introductory part, clock basics, what makes a clock, what clocks are at the moment with their best qualities on the market. Then I will introduce you to the properties of thorium-229, also talking about which applications we can expect from such a nuclear clock. And then in the main part, I will talk about our measurements on this famous isomer, about the first identification, direct identification, I have to say, then about the lifetime measurements, and most recently also laser spectroscopic studies that gave us some hints about the internal structure. And I will close to a summary and tell you about what we are doing, what comes up. The story has not yet ended, so there is more to expect in the future. So what makes a clock? Very basic. We need two things. We need a periodic event. We need some oscillatory event, and we need something that counts the oscillation. So a counting device and some oscillation makes together a clock. And if you look for very basic examples, we have, as a rotation, for example, the rotation of the Earth or the moon phases, which make up then the sundial as the counting device here. And if we then increase the frequency, we go also in history to the pendulum, to the spring for the mechanical clocks. We have the quartz crystal as an oscillator for digital clocks. We have atomic transitions. Now we are already in modern times for the microwave realization of time, or the laser for the more modern optical clocks. And here comes now the question in the game. What about a nuclear transition instead of an optical atomic transition to be the basis of such a clock? Well, which type of clocks do we know? Very trivial. Everybody probably has a mechanical clock with an accuracy typically of about a second per day. The world record, realized at least in the US, is about 1 second per year. Digital clocks, very cheap, available, with an accuracy of about a second per month. And the world record here, the accuracy level already on the level of 10 to the minus 12. So that's already amazingly good. But now we come to the standard, what our time is defined on. Atomic clocks, the accuracy here is on a level of 10 to the minus 14, and the world record, not by such a device here, but by an optical lattice clock, which is a laboratory-based device at the moment, the world record is about 10 to the minus 18. And still we think a nuclear clock based on thorium-229 could do better than that. So that's the challenge, and that's the framework we are working in. If you operate a clock, you want to have it in a continuous feedback-like operation mode. So you want to have your atomic transition stimulated and interrogated with an optimum energy transfer at its specific excitation frequency, the clock frequency F here. And for that, you find such a resonance curve where the excitation frequency is here the centroid. And then you define a quality factor, and this quality factor says, well, what makes a good clock? A good clock is if you have the highest oscillation frequency. You want to shift this to very high frequencies. That's why at the moment optical frequencies are pursued. And you want to make it as precise as possible, meaning you want to have this resonance curve to be as small as possible. So high frequency here, small width of the resonance curve makes a good clock. And the numbers for the microwave clocks, the one which make our standard atomic time on the order of 10 to the 10 for this quality factor. For the optical atomic clocks, we gain about 4 orders of magnitude, basically by driving up here the frequency from a microwave frequency to an optical frequency. And the nuclear clock at least holds promise to gain another order of magnitude here for this quality factor. Now comes the question, and always when I talk to that, for example, in school classes, why do we need better clocks? If I'm on time at the seminar here, why would I need a better clock? There are several reasons. One would be an academic answer. Every time that better clocks were invented, every time that the clock precision has improved, there would be new and even unexpected applications to pop up. But that's probably not convincing for somebody who wants to, or who's asked to finance it. But there's another application here, which is obvious to all of us, I guess, which is satellite-based navigation, the GPS navigation, for example, where present technology relies on the microwave-based atomic clocks on rubidium or cesium. The GPS system from the US, the Russian system, they are active already. Galileo from Europe is just being in the finalizing phase. The Chinese and the Indian system under construction, all of them are of the order of a few meters positioning accuracy. That's what.
Sometimes more, because you can use also interference effect of.
Yes, 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 you're right. But in general, the goal is what would be to bring down this from the meter level to the centimeter level or even below. Of course, that's a dream here in the millimeter. Then you could think of applications which are widespread, from autonomous driving, freight component tracking, and you name a list of other things. What you need for that is, well, better clocks in a sense that one would aim at this 10 to the minus 18 that are actually at the moment already in the lab accessible, maybe even better. They should be low, small, robust, low power consumption. And something I want to point out explicitly here is they should have a long-term drift stability, because if you want to have it in a reliable industry-based, let's say, operation, you don't want to put them out of order, let's say, for resynchronization for maintenance periods. So you want to have them operating continuously over a long time. You want also to avoid costly redundancy. And that is something which in the end will also be a beneficial issue.
Which units are for those 10 to minus 16 and minus 18?
And that's relative units, that's accuracy. Yes, because this is not a unit anymore, this is a ratio, that's accuracy. Let's say that's delta F over F, something like that. Or, yeah. So it's the accuracy, it's the precision. It's not, well, if you, let's say, if you have 10 to the minus 18 accuracy, then you have about 1 second, well, going, your clock will go wrong by 1 second in about 15 billion of years. So longer than the age of the universe is 10 to the minus 18. That's the order of magnitude we're talking about here. Okay, so then there are some even more exotic applications that you find in literature. If you look, one could use networks of such clocks which you place around the globe to search for dark matter. But not for the dark matter as we know it, or as we think to know it, which is isotropically more or less dispersed in the universe, but of the so-called topological dark matter, which is clumped in monopole-like or string or domain wall arrangements. Of course, this is a theoretical construct. It's published a few years ago. But if the Earth carrying those clocks would pass through such a domain, it would change the synchronization of the clocks, and that could be an indicator. So this is certainly something which sounds very exotic. More down to earth is a different type of application, which is also pursued, of course, in optical lattice clocks, to use them as 3D gravity sensors. So you relate the shift, the difference of a clock frequency to the difference of the gravitational potential. And with the present, the achievable best clocks, you detect gravitational shifts of about plus minus 2 centimeters. So if you lift the clock up, you will feel the change of the gravitational potential. The clock will have a different speed, so to say. And now you could use that, what is called in the literature relativistic geodesy or chronometric leveling. So you could map the potential field, the gravitational potential field of the Earth on a fine grid. At the moment, this grid is mapped by satellite missions to about 100 kilometers squares. So this could be reduced a lot. And what could be then pursued here is, for example, look for local changes of the gravitational potential. For example, if a volcanic magma chamber fills up, which could be an indication of a soon-to-happen explosion or eruption of a volcano, or if you see that tectonic plate movements appear on the level of a few millimeters long before there would be then an earthquake happening. So this is something, of course, can be done with the optical clocks as well, but hopefully with improved precision, improved accuracy than with a nuclear clock. So those are some of the applications why nuclear clocks are interesting. But now coming back to a fundamental point of view here, there is something which is always discussed when we talk about nuclear clocks and thorium in particular, which is the question, how constant is a fundamental constant? So time dependence of fundamental constants is something which is, well, proposed in some theories. You need some grand unifying theories where you find that it suggests temporal or even spatial variations of some fundamental constants, specifically the fine structure constant or the strong interaction parameter, basically the quark mass parameter here. There's a whole bunch of literature over that, basically initiated by Victor Flambaum from Sydney and his collaborators. And they claim, at least, it's not just a small sensitivity enhancement here, but it's several orders of magnitude that one could expect to gain if you would look for temporal variations of the transition energy of thorium and then increase your sensitivity. Well, what is thorium giving you here? It has this doublet, this ground state doublet of the ground state and the almost degenerate isomeric state, the first excited state. This comes from the small difference of the Coulomb energy. The Coulomb energy, of course, in such a heavy nucleus is of the order of giga-electron volts, and it almost cancels. And since this Coulomb energy depends on the fundamental constants, any variations would be enhanced in the thorium transition frequency, but the present limit of such, for example, temporal variance of the fine structure constant is of the order of 10 to the minus 17. So you had to measure either very long or with a very high precision, but then with a constant, stability of your apparatus. So you need more sensitivity to bring that small effect, if it exists at all, into a measurable time of a few weeks, a few days, or something like that. So this could be something which is for the future also an aspect to look into here, and to say what is happening here or why is thorium so intriguing. You relate, for example, a relative change of the fine structure constant to a change of the transition frequency in thorium. So this is the thorium transition frequency, and this is the difference of the Coulomb energy of the isomer and of the ground state. And so you can relate a relative change of the transition frequency to a relative change of the fine structure constant by introducing this enhancement factor K, which basically is the fraction here between the Coulomb energy difference and the laser transition frequency. And this has been, of course, studied or can be calculated as well for the traditional clock isotopes here. And here you see optical, isotopes and atomic transitions which are used for optical atomic clocks, and you see their transition wavelength and their enhancement factors, which are typically small but not exceeding a few tenths. But here you see for thorium this value is by orders of magnitude higher than any of the others. And the problem is just that you cannot calculate that reliably, since you would have to calculate the Coulomb energy, the nuclear Coulomb energy, which from the nuclear point of view, in nuclear models, which are not adapted to the precision of electron volts, as you know, the energy scale in atomic physics is electron volts, while in nuclear physics is kilo electron volts or mega electron volts. So theory in nuclear physics has never been tailored and will never be tailored to electron volt precision. So it cannot be calculated with this insufficient accuracy, so it needs to be measured. That brings us back that we have something which is potentially interesting here, but verification is only possible really by experiments. And that makes us now going in the direction to look to thorium-229 in more detail. What makes it so unique? Why is it really so special that people searched for it since more than 40 years? And for some time it was like chasing a phantom. So people were looking into, but never there was a direct observation. There were indirect hints. And you saw in 1976 it started. There must be something. They concluded on spectroscopic findings at the time. They could not give could give a threshold for the energy, and then it was refined over the years. For many years, it was also in the literature called the 3.5 electron volt isomer, and people were looking at the time then with optical technologies into that, which was a pity. Well, okay, you can only do what you know at your time. But then in 2007, this energy doubled all of a sudden into 7.6 electron volts, which shifted the wavelength region from optical into vacuum ultraviolet, which means nobody looking into optical properties would have ever discovered that. So, and at that time, then we started also to get interested. And now, what is known, what is the expected properties of thorium from indirect evidence at the point when we started was the electron volt, well, the energy, the excitation energy is 7.8 electron volts, which in optical terminology is about 160 nanometers. So in the vacuum ultraviolet, it's an isomer with a radiative lifetime of a few thousand seconds. This is also not measured. It's from M1 systematics. You would expect that because it's an M1 transition. And the point is here, which makes it so intriguing, the relative line width is about 10 to the minus 20. So the frequency width of the transition 10 to the minus 4 hertz. So this really makes it a candidate for a very precise standard of time. Basically, this first excited state of thorium-229 is the lowest excitation energy of all about 176,000 presently known excited states in the landscape of isotopes. So we know about 3,000 isotopes. They have this number of excited states. And in this plot now, one of my students has compiled all the isomers that you find in the databases. So all nuclear isomers, and you see here the excitation energy versus the half-life. And you see here that this is 100 keV, this is 1 MeV, so this is a typical energy scale of nuclear physics. Here we are in the electron volt region, and here you see the red dots. Those are those nuclei, those atomic shell transitions which are used for optical clocks, and then you see this blue bar here, which is thorium-229, by orders of magnitude separated from everything else which is nuclear, but lying exactly in this area where the optical clock transitions are located. And just to name this guy here as well, it's the next high-lying or low-lying first excited state, the next isomer in uranium-235. It has a factor of 10 higher energy. It would still be very difficult to excite that optically, but it has by orders of magnitude larger radiative lifetime, so it would never qualify as a frequency standard. Just to show that, I will come back to this point in a few minutes. So here we bring thorium in the vicinity of optical transitions for clocks. What makes it so interesting is that a nuclear transition is extremely, well, it's shielded, or it's just immune against external perturbation because the nucleus is so small compared to the large shell. So external fields just have, because of the small nuclear moments, no leverage, not so easy leverage at least, to perturb the transition frequency. So it's largely immune here, and by that could also qualify for ultra-precise frequency standard. To show what this measurement in 2007 brought about when the energy changed from 3.5 to 7.6 electron volts, this was actually done by a microcalorimeter, so a semiconductor detector measurement, an X-ray detector measurement. They were not looking at the excitation energy directly. They could not measure that. But what you see here you have the ground state band, and here you have the excited state. So ground state, isomeric excited state, almost degenerate just by about 7.8 or 8 electron volts apart. Then you have rotational bands on either of the two, and you see here that there are energies, 40 keV, 50 keV, which then were resolved. So what the people looked at were the rotational spectroscopy transitions at high-lying states, rather high-lying states, which then, if you do the double difference between those transitions here, in-band and out-of-band transition at 42 keV, or here 29 keV, and if you make this double difference here, what remains is just the energy difference. So that was the only indirect evidence that one could hint at this, well, not just at the existence was already in 76, well, concluded from spin and parity assignments and from the consistency of spectroscopy, but the energy came from this very indirect, subtraction of large numbers and then remaining with this difference for the excitation energy. So now we got interested, what could we do? How could be a concept, if you don't know how to excite it from the bottom, how would you populate this isomer? And there helps nature very much by just providing uranium-233, which is an alpha emitter. Uranium-233 makes an alpha decay, -4 goes into thorium-229. And the good thing about this, that it doesn't go by 100% into the ground state, but via a 2% decay branch into the excited state. So 2% of the alpha decay populate the isomer, and then the idea was, let's spatially decouple the population from the de-excitation, and by that get rid of many background components, and then wait for the isomeric decay at a remote place from its production. And that brings us now to the concept on how to set up the experimental system. So what we had at the time, and that actually was a starting point, was a so-called buffer gas stopping cell. So that was developed for fusion reactions, for super heavy elements at GSI, and we had many different purposes where such a system was used, but now we thought, well, it could just be the right device to use it for this application. So what you have here, you have a vacuum chamber, you put a uranium-233 source in there, and what you see here is a decay chain of uranium-233. Don't look at all the details, it's just the alpha decay of uranium doesn't give you only thorium-229, but also all the subsequent daughter products of the alpha decay. So for like radium, francium, astat, bismuth, lead, all they come with some recoil velocity. So the alpha recoils go into an atmosphere of ultra pure helium, which is inside this chamber. Then you have electrical fields, radio frequency and DC fields that in a funnel-like structure will channel the ions. They stop them first, like with an airbag, you bring them at rest, and then the electrical fields drag them into an exit nozzle, so there's a hole in this chamber, and then a supersonic jet is formed. The supersonic jet rips the ions off the field lines, drags them into the next vacuum chamber. This is a radio frequency quadrupole, an ion guide, where the carrier gas is pumped away, and then the ion beam is formed. It's also cooled here, phase space cooled. Of course, now we have to get rid of all the accompanying daughter products, which are not thorium-229. So the next part is a quadrupole mass separator, which then blocks all the daughter nuclides and then only leaves thorium in various charge states in the ground state, but also in the isomeric state, to be then focused by an exit electrode system. And then what we at the time were planning to, what was, I think, obvious, that we would like to collect the ions somewhere and then wait for their isomeric decay, looking for the photons coming out, the UV fluorescence. So we built up a fancy UV detection system from two annular parabolic mirrors where the collection electrode was in the focus of the first mirror. So whatever would come out as photons here would then be collimated parallel to the second mirror. The second mirror was so deeply cut that a detector system behind was here in the focus of this parabola. So you would focus everything onto an MCP, a microchannel plate detector, would there generate secondary electrons. Those electrons would be accelerated towards the screen and then looked at with a CCD camera. So that's the overall detection scheme. And so does it look like in reality. So you have here the buffer gas cell where you have this funnel-like structure, for example, inside. Then there is this 4-rod quadrupole ion guide. Then comes the quadrupole mass separator in the third box. And then in the end, after the optical detection system, the microchannel plate for the final detection of the electrons looked at optically with a CCD camera. So that was then the status. Then we wanted to check what do we extract from our gas cell? What comes out if we extract all the recoil ions? And we had to make sure that we are really extracting thorium, and this is the mass scan here from low masses, mass 10 up to mass 300, and you see one group of ions here, another group here, another group here. There's a singly charged, doubly charged, and even triply charged ions. Of course, we not only see thorium, but we also see uranium from the source, and just assume now for singly charged, doubly, and triply charged ions. In charge state 1, we have a little bit of thorium, and most is uranium. In doubly charged, you have on equal intensity thorium and uranium, and we even saw a maximum of the triply charged, which has never been seen before at that time in a charge state 3 extraction from a gas cell, which had a certain physical reason, which I shall immediately tell you. But here you see we have about 15%, so 5% in the 2+, 10% in the 3+ for thorium, and then all the others here also quite abundantly. Francium, for example, 16% in the 2+. So there comes a lot of these byproducts, the daughter products, which have to be then eliminated by the mass spectrometer, and they can be efficiently eliminated. But now the question, why do we see at all the 3+ here? Because we are in a lucky situation that we have helium as our buffer gas. Helium has an ionization potential of 24.6 electron volts, and only in this mass range, only for uranium and for thorium, the 3+ ionization energy is below the 1 of helium, which makes it energetically favorable to stay in the charge state rather than make a charge exchange reaction here. So only for uranium and thorium you can expect at all to extract a triply charged ion. And this is very important for us in the future. Yeah, now we have this detection process that I showed you. And we had the VOV optical detection system designed, we had built it, we had commissioned it, and we operated it. And we were now in a situation that from our simulation, we expected to see, well, a UV photonic signal well separated from background with a good signal to noise ratio. That's really what we were able and hoping to realize. But then came this moment of despair, and we didn't see anything. No photons, nothing came. First of all, we thought, well, something is wrong with the apparatus, of course. Then you think, well, maybe the alignment is not okay, your extraction doesn't work, but nothing of that worked. And after some time, we thought, well, there will be, probably there is a physics reason behind. And that is exactly what we came up then. What if the excitation occurs predominantly radiationless? Is there any chance that the excitation energy from the excited state can be emitted without emitting a photon? So is there an alternative decay branch? Yes, there is. And it's internal conversion. So the nucleus can transfer its excitation energy to an electron from the atomic shell. and by that avoid to emit a photon and then emit an electron instead. And I will show you why this is possible and under which conditions this is possible. So what we had to do, we had immediately to switch our mind. We should not detect photons, we should go for electrons. And that's exactly what we were doing then. So drop 1.5 years of development here. Just implant the ions directly on the MCP surface and look for the electrons. That is exactly now the strategy that we're pursuing. So we come with a triply charged thorium isomer onto the surface of a microchannel plate detector, which is a double plate, a chevron-like geometry here. So in these channels, you multiply the electrons in this. Yes?
My question is, what way you make the ions in excited state? Do you excite them in any way?
No, the ions are excited in 2% of the cases directly in the alpha decay. So the population process is the alpha decay. What we are aiming for, of course, in the future, that's why we are doing all that, to learn more about the energy. Ultimately, you want to have an optical control. You want to send with a laser from below to the ground state, but for that, and I will show you what that really requires, we need to know the energy much better.
Excuse me, could you correct me if I'm wrong? It means on the nuclear level I can obtain this isomer, and after that I separate it using this quadruple separator, only this type of ions which are on the level.
No, you cannot separate between the ground state and you select a mass over charge ratio. You don't select an isomeric specific beam. You have thorium, which is, but the decay, the half-life of the ground state is close to 8,000 years. Even if you have a dominant extraction of the ground state, you will never see anything which is competing to what you expect from the decay of your isomeric state. So here, now we have a situation where we have to be careful. Now we come with accelerated ions that fly towards the surface of our detector. Now we have to make sure that, and we want to measure electrons. We have to avoid that now banging this ion into the surface here by the ionic impact liberates electrons, and they together with the decay electrons make up a mess, and we don't know what we are doing. Is it ionic or is it really decay? So that's why what we realize a soft landing mode. So let's say we bring this surface here to a very soft accelerating potential, minus 25 volts, then we accelerate very strictly towards the screen here by a few kilovolts, but the landing on the surface has to be very soft, and I will show you what that makes in the end. Then, so once the ion hits the surface, what will happen? It will see a sea of electrons in the surface. It will neutralize. It cannot do anything else. There are electrons, and the 3+ will neutralize. And now, this will now exactly be the situation where we have to think, because now we are in the situation that we have an ionization potential of thorium of 6.3 electron volts, which is smaller than the excitation energy, presumably at least, of 7.8 electron volts, which means the internal conversion decay channel is open. It's energetically allowed. And whenever it is energetically allowed, it will also be the dominant channel. Because from theory, and there are papers on that, which we will check later on, this conversion factor is huge. It's of the order of 10 to the 9, which means the lifetime should be reduced from an ionic state of a few thousand seconds to several microseconds in the neutral case, 9 orders of magnitude. So only if you manage to suppress the internal conversion channel, then you could think about that to see any photon. On the other hand, you would have then to compete with a channel on the order of 10 to the minus 9, which is pretty hard to do. So then you would have this electron cascade, which then would be multiplied and which then would be accelerated towards a phosphorus screen. And then in the end, you look at that, you create visible light, and from a camera, you look at it. And this is now exactly what we saw. And when we saw this, we really couldn't believe it. it was immediately we saw such figures. Now what do we see here? Again, the mass spectrum here in the triply charged, doubly charged, and singly charged. And now we set our quadrupole mass separator to selectively guide thorium 3+ or uranium 3+ or thorium 2+ or uranium 2+ for 3 different sources. So we are in our measurement process, which went over 2 years, we took here a weak uranium source and a strong uranium source. And you see for thorium, we get a weak signal here for thorium 3+ and a weak signal for thorium 2+ for the weak source, and we get a strong signal for the 3+ here in the strong source and as well for the 2+. That's actually exactly the figure that we get from our CCD camera. But that's an optical, that's visible, that's light, that you can directly see on the screen online. Well, and then we had to convince ourselves, couldn't that still be something that comes from the atomic shell? What would you do? We changed the source and we used uranium-234. Uranium-234 also alpha decays into thorium-230, which has the same, in principle, nuclear situation, but in principle, well, it's a different nucleus, but to say the same chemistry, so to speak. So if there is anything there which comes from the atomic shell, it should be visible. If it's from the nuclear point of view here at the excitation, then you wouldn't see anything. And exactly that's what we have. So in a neighboring isotope, it's completely quiet, while as we expected, we see from thorium a strong signal and a weak signal here, and a strong and a weak source. Nothing from uranium, as we expect, because there is no isomer in uranium. And you see it has a beautiful signal to background, so undoubtedly there is a clear signal. Still, we're doing quite some verification measurements to convince ourselves that this is really what we think, the de-excitation of our isomer. So we changed the attractive potential of the surface of the microchannel plate detector from here -100 volts to up to 0 to threshold, and we extracted thorium and we extracted uranium. You remember, initially the doubly charged were extracted from the gas cell at equal intensity. And if we now, and here's the count rate that we measure, if you now crank down the voltage from, well, quite accelerated with ionic impact, you see there is quite some rate, but as much as you lower the attractive potential, it goes down to 0 for uranium, while it stays at some decent level if you do it for thorium. So as expected, when there is no isomer, you crank it down, and you can really, by realizing this, what we call soft landing, the small accelerating potential, avoid any ionic impact signal. And another proof here, you do that in 2 different scenarios. One time the soft landing mode -25 volts, and here heavy acceleration, strong acceleration, -900 volts. In that sense, we really, well, prepare the pure ionic impact signal, which gives us here the blue curve for thorium and for uranium, as we expected from the mass spectrum on almost equal intensity. So that is only ionic impact. If we do the small accelerating potential, if we just let it very softly drop onto the surface of the microchannel plate, this peak goes away. We are still left with the thorium signal, and we even see something at the very end here, which is just the mass of the 235 uranium, which I showed initially, the second isomer that exists in nuclear physics with a low-lying energy, of course not usable for a nuclear clock, but very consistently showing up also in this representation here. So we see the thorium signal where they should be, uranium drops to 0. So now we really convinced ourselves that we see for the first time the direct de-excitation of this isomer, and all potential background contributions could be excluded. We did many tests, and don't talk now about the radiochemistry of the sources and all this consistency checks. So it took us more than a year to convince ourselves before we were publicly talking about that this signal is really coming from the nucleus and not from any other background process. So having done that, the story goes on. What would you be interested now that you know the isomer is existing, we measure, we know which channel has been populated. Now we want to learn more about the decay properties. Now we look into the decay in the half-life, for example. Of course, here you have schematics of the situation, the gas cell with this funnel structure, the source that sends the ions here towards the quadrupole and the separator, finally towards the detector. If you have it charged, what we can do a pulsed extraction. So our ion guide here is segmented, so we can use it as a linear Paul trap, and we can use it in a sense that we lower the potential, accumulate some ions, and then lift it up again, and then extract a bunch of ions, and then look what is shown at the detector. Now we hit the barrier, and the barrier is a lifetime of about 1 minute. We can only tell that whatever comes charged here lives longer than a minute. Why? Because this is just a usual room temperature high vacuum equipment, 10 to the minus 7 millibars, which limits the lifetime of ions to lower than a minute. We are just limited by the vacuum quality of our apparatus, not being able to measure those expected a few thousand seconds of storage time in this simple arrangement of the linear Paul trap. So we can only give a limit here, but of course what we can do, we can, as we do before, we can impinge them on the detector, they will neutralize, and as I told you before, now the internal conversion decay from the neutral atom should be reduced by 9 orders of magnitude in the lifetime. So this should be possible to measure. And that's actually what we are after. So we expect a conversion coefficient of about 10 to the 9, which would then really give the constraint of why people didn't see the photonic decay branch so far if they cannot suppress internal conversion. So what we did here, we first simulated that. We simulated here in red the ionic impact, so a pulse which has a width of about 10 microseconds. That's what we realize in our Paul trap. And then we send this pulse of 10 microsecond width onto a detector. And if we add an isomeric decay in the simulation, we just get here this decay tail that adds on top. So then we have isomeric ionic impact plus exponential decay. This is how it would look like if we assume, let's say, 7 microseconds for the decay, which was just a guess from the 9 orders of magnitude, which we expect for the conversion coefficient. And this is the measurement. Here we have 10 microsecond pulse width. We extract a few hundred thorium ions per pulse. And now blue means the thorium extraction, triply charged. Red is the same triply charged for uranium. The difference in this edge here is just the mass difference, the flight time difference by the mass of 4 units. And you see in uranium, where you don't expect an isomer, you only see the ionic impact signal. While nicely, as expected from simulation, you see the exponential decay from the thorium from the isomer. Of course, you can again check that by varying the ionic impact, by varying the acceleration voltage towards the detector system. So we reduce that from 350 volts down to 50 volts. And what you see here, you only affect the height of the ionic impact, while the decay, the isomeric decay, is unaffected by that. The more you reach the soft landing, the more you reduce the ionic impact to bring it to 0 finally. And the decay here of the isomer is completely unaffected by that. Now you want to quantify that. Of course, we can do the next check, which we also did before. Look at thorium-230, which is now the neighboring isotope, which has no isomer. Again, only the ionic impact signal, while for thorium-229 in the triply charged state, we see nicely this exponential decay, which you can then fit and extract a number. And smack on, it delivers the value that is from theory expected, 7 plus minus 1 microsecond. It completely concurs with the 10 to the 9 that we expect for the conversion factor. So this was really very nice to see how well this confirmed what was expected. So now we know the neutral lifetime, of course, in the, yeah?
Can you comment on the shape of the decay? why it is such a kink? There is such a kink on the.
Well, this is still the ionic impact here on the front, and then after that you see the exponential decay, the short-lived. So this is just well, I don't know at which voltage that was done, but here certainly maybe at 100 or 50 or 100 volts. So you still see here, and we wanted to have that deliberately, that you see both components at the same in the same plot. We could also have cranked down the voltage that you don't see this component here at all. But we want to compare thorium-230 with thorium-229, showing that ionic impact is what you get if you have a high acceleration voltage, but then you have something extra which you will never get if there is no isomer expected. Yeah, now, of course, and I would have loved if I had been able to tell you already today also about the energy, which I call the holy grail of this whole business, so the excitation energy. We were very conservative in our publication just to constrain it between the first and the third ionization potential. This is just what we safely can tell. The experiment was never tailored to be selective for the energy. It was just a discovery experiment. But now, since quite some time, we are working on the energy. And what are we doing? Now we know that we have to look for electrons. We have to measure the kinetic electrons of few electron volt electrons because, well, excitation energy is around 7 to 8 electron volts. You have the ionization potential of about 6.3, so there is not much kinetic energy left. And you have to measure this very small energy to very high accuracy in the competing presence of other channels. So that's not very easy. So we take a magnetic bottle spectrometer. That's what we are doing now as a technology. Because it offers a large angular acceptance, we extract about 10,000 ions per second. 2% of them are in the isomeric state, so we get about 200 electrons per second, and that's a scheme of the setup. So we have here the ions coming in. We have a catcher, a solid state catcher surface in an inhomogeneous, from a permanent magnet produced magnetic field. Here we induce the internal conversion decay, and the electrons will then be focused into this direction, into the magnetic bottle spectrometer, which is a coil system, where they spiral towards, at the end, a microchannel plate detector. But in between, there are blocking electrodes where we can scan the blocking voltage, and only those electrons with the kinetic energy higher than the blocking voltage will make it to the detector. So that's the same principle which is used in the Katrin spectrometer to measure the mass of the neutrino by retardation. That's just a miniature version of that. Of course, still we have the issue here that we still have maybe solid state effects on the surface, which makes it difficult. That's why we upgraded now the system to a different arrangement. We think we can avoid all ambiguities by working only non-invasively, without any contact, by neutralizing the ions, the charged ions here in a carbon nanomembrane, let them fly through. With a certain percentage, they will be neutralized here. And then we have deflecting grids, which just, well, all the still charged ions will be deflected, only neutrals will pass by. During that time, they will start decaying with 7 microsecond half-life. And they will decay here in the acceptance of the spectrometer. And some of them, of course, we lose some efficiency by this concept, but we gain by ambiguity, removing any solid state catcher surface. And then we go towards the detector in the end. That's a very simple system. It looks like that. And what has been simulated and what we expect between 50 and 100 millielectron volt resolution in the end, energy accuracy. That's what we are aiming for. We are measuring. I cannot tell any numbers right now, but maybe in half a year, we are in the way. So we are working on that. If we know the energy, then comes the next step. Then we would like, to build a laser system that is then possible to do the optical excitation. And then we can use an old scheme that already 15 years ago by Eckhard Pike and Tom was proposed, because then you could use something like a double resonance or Demel shelving method to detect whether you do this excitation. Whether you have a laser is still, how would you diagnose that you did the excitation from the ground state into the excited state? And the scheme is shown here. So you have nuclear and electronic degrees of freedom. So this here is the ground state, here is the excited state. Now we have two electronic transitions here. So we tune one laser on resonance, that is omega 1, on an electronic transition in the shell. Then we do now with a laser that we are still working on, which needs the right excitation energy to transfer from the ground state into the isomeric state. So then we are in alpha prime, which is the isomer, and then we have still the electronic situation in the shell, but now we have changed. We have changed the nuclear situation, we have changed the nuclear moments, the spin, the hyperfine splitting will change, the overall angular momentum will change. So omega 1 will be out of resonance, and the resonance scattering will just drop. And by not seeing the resonance scattering from this transition here anymore tells you did an excitation. Of course, you have to know the hyperfine splitting for that, to diagnose that. And that brings me now to the last part, which is our most recent achievement here. So now we were teaming up with a group, actually the group from Eckhard Peik, who was proposing this 15 years ago, who is the master of the German time. He's at the Physikalisch-Technische Bundesanstalt, the German Metrology Institute, and they are, well, experts on laser spectroscopy, and we were teaming up with them. So we were providing our isomer beam, our setup here, and they were bringing all their laser equipment in a big truck into our lab, combined that, and we were doing collinear laser spectroscopy on the thorium ion by some diode lasers with co- and counter-propagating experimental scenarios. They did already in their own Paul trap at home some preparatory experiments, so one had already some idea, at least in the ground state, how the hyperfine splitting would look like, but of course no idea how it would look like in the isomer. So what was done here, one had again the schematic picture here, the gas cell, the source, the funnel structure. Fortunately, not planned initially, but fortunately our source has a hole in the middle, which came up pretty handy here, because now we could send our laser beam through the source on axis here, co-propagating or counter-propagating. We were choosing a two-step laser excitation, Doppler-free laser excitation. So two laser colors were sent in. The first one here, bluish color, just from the ground state, takes a certain fraction of this broad Doppler profile of all the velocity classes. Only one class is excited, into an intermediate step, and this is done in 35 different steps. And then this intermediate stage is then probed by a second excitation here in the infrared into a final state, and for each of those steps here, this laser is scanned over 4 gigahertz and then searching for the respective transitions that come from the hyperfine splitting. So what you would expect here for the ground state, which is a nuclear spin of 5½ you would expect 9 hyperfine components, while for the isomeric state, 3½ you would expect 8 hyperfine components. You would look then for the fluorescence. You had some fluorescence detection here, which of course is in a different frequency range than the initial lasers, not to mix up with stray light. We had a third laser, again at a different laser energy, to monitor in a single-step excitation the amount of ions in the trap to have a normalization of the fluorescence, so to have everything also quantitatively under control. And what we measured then is finally such spectra here. So in red, you see the ground state, and in blue, the signal that comes from the isomer. Those peaks here in cyan, they are actually the first ever measured nuclear states from the decay of the isomer in the hyperfine splitting. Those is just 2 exemplary figures out of more than 70 that we have in co- and counter-propagating detuning of the first laser. There is one detunement, there is the other one. So all of those states turn up in one or the other arrangement. So finally, we get all of those hyperfine components from the ground state, from the isomeric state. This allows this from this hyperfine splitting formula that you learn from textbooks to extract the hyperfine constants A and B, which then allow you to extract quantitatively the electrical quadrupole moment, the magnetic dipole moment, and the charge radius. So 2 years ago, we didn't even know that the isomer was existing. At least we were only suspecting it from indirect evidence. And now we are already quite deep in the nuclear structure and quantitatively assessing what is happening in this isotope. So this brings me to my summary. So I showed you that thorium exists, the thorium isomer exists. The first detection was successful by internal decay spectroscopy, internal conversion. The constraints of the properties from this first measurements, well, coarsely but conservatively between the first and the third ionization potential with a lifetime of more than 1 minute, but this still can be improved, as I will show you. The half-life of the neutral thorium was measured to be 7 microseconds, confirming the conversion coefficient of 10 to the 9. We did collinear laser spectroscopy for the nuclear moments, charge radius, measuring the prolate deformation. This will, in a few weeks, appear in Nature as well. Then we are measuring with a retarding field bottle spectrometer the isomeric excitation energy, the method we have published, the values we are working on. So we still need a little bit more time for that. And then another activity that we are doing, and with that I somehow contradict myself, telling that we always need to do the optical excitation, a better knowledge of the excitation energy. This is true for the final application of the clock, where you want to have the optimum laser tuned exactly to the transition frequency, while for a general feasibility study, we have shown in this publication here that it's possible to do it already with existing laser technology. The trick is you have to take the decay channel that we now identified, the internal conversion decay channel series, and you have to take a tunable pulsed laser system in the VUV, which is existing, and you have to trigger the detection of conversion electrons, not of photons, with a laser pulse. And by this coincidence, you get rid of the background, and you can get a very good signal-to-background ratio, and you can, even with existing laser intensity, finally come to a point that a scan of an electron volt, which is sufficient, can be done in 3 days. So this is a feasibility study that we'll still do this year, I guess. The charged thorium, which needs a longer storage time, as I told you, well, for that we are setting up a cryogenic Paul trap, which will give us access to this long lifetime, but as well then be the backbone of any further laser manipulation towards the final goal of the nuclear clock in a suitable environment, in a contact-free stored environment of a Paul trap. So what we did, we think that we made a big step forward towards the ultimate goal, which is not just around the corner, but we are approaching that. So the optical control of the clock transition, something like Maria Zavranova called that still searching the needle in the haystack, but we know now much better how the needle looks like, and we are working on that. And with that, I want to give thanks to the people contributing to the study, specifically to Lars von der Wense and Benedikt Seiferle, the 2 PhD students, not anymore. Lars is now a postdoc in my group. They took really the most of the work here, and Steel King and Pavel Blavatsky, they were working from the PDB measurement on the collinear laser spectroscopy. And with that, I want to thank you for your attention.
Thank you, Peter, very much. So now we have time for questions. Yes?
I have a following question.
I have a question. What would be a construction of this clock if everything would be okay? Is it the same as for cesium clock or some differences?
Basically, you have 2 different ways how you could build it. Either, as I indicated vaguely at the end, you put it in the vicinity of something like a cryogenic Paul trap, where you have it stored, where you manipulate it with different laser beams and interrogate it in this contact-free environment. Mm-hmm. This is one thing. You would probably do it in the 3+ state, because this is a noble gas-like +1 valence electron configuration, so very simple to laser cool and very simple to deal with. So that's one situation. And then you would still have quite a sizable apparatus, more or less like the present nuclear atomic clocks also, as you see. They are quite bulky environments, but there are not more than 260 worldwide of that. Yeah. The intriguing thing would be if our colleagues would be successful, who since several years try to do it in a solid-state-based approach. So they take a UV transparent, let's say magnesium fluoride or calcium fluoride crystal, dope it with uranium-233, put it on some lattice-sites. The band gap is larger than the excitation energy, so by that, at least theoretically, internal conversion should be prohibited. And if you put it really on a lattice site, also the charge state of the ion should be maintained. And then you bring it in the radiation field of a synchrotron light source, could be broadband, and pick up the right frequency and get the fluorescence and get the excitation done. Then your clock in the end could be a little crystal. Mm-hmm. Unfortunately, people were doing that and are doing that since years, and other than just looking at radioluminescence or Cherenkov radiation from impurities, they didn't see anything. So my personal conviction in this point is the crystals are not perfect enough. They still have contaminants. You cannot obviously good enough suppress the internal conversion. I cannot state whether this will be a permanent situation or whether it can be improved. At least they will continue towards that. But this would be the most elegant way to realize the nuclear clock.
Thank you very much.
Other questions? Gilek?
Small comment and question. We met, I think, more than 3 years ago in Zakopane. So to me, you performed such an enormous jump forward in this. It was such a big difference when I remember your talk in Zakopane nowadays. So my simple question, how big activity of uranium you need to perform all of these things?
3 people. And to me, it's a side activity.
Your question was concerning activity of uranium.
Uranium activity.
Uranium, yeah.
260 kilobecquerel, which is the point is that we are looking at alpha, at the alpha recoils. So what you need to have a very thin surface. For that, you need to spread it out. And you need to have a technology to do that in a reliable way. So you have only 17 nanometers, so you have a recoil energy of 84 keV. The travel path through uranium in the bulk material is about 16 to 17 nanometers. So you have to be very thick, very thin, and spread it out. That's what we did. That's why we have 2 different sources. The weak one was actually not weak. They had the same activity, but it was too thick and smaller. And the second one was larger and thinner, and that's why we got the higher activity. If you do the laser experiment, it will be negligible, because there we don't use uranium anymore, because if we do the laser experiment, we directly shine in laser light on thorium. And thorium only with a surface area of the focal size of the laser, which is a few microns, so we will have actually just 2 millimeter diameter, and we will have only 2.5 nanometer thick material coated onto this, on a reflective, UV reflective mirror. So that's probably becquerels. It's nothing. And in the end, I would say you will never exceed the legal exemption limit if you would operate it with thorium with an optical excitation. And that's actually the goal, to have it in any laboratory operated below the legal exemption limit.
Yes. Wait a moment for the...
You mentioned 3 lifetimes in your talk. One was 10 to the 4 seconds, one was 60 seconds, and one was 7 milliseconds.
Yeah.
And microseconds. And I don't really understand which one is which one concerns what. So which one is the lifetime of the isomer, and does it depend on the surrounding? It
depends on the surrounding, yes. So if you have your isomer in a charged ion, then your internal conversion decay is blocked, and the radiative photonic decay branch is the dominating one. And then your lifetime is what is expected between a few thousand and 10 to the 4, a few hours.
So that would be for neutral atom?
No, for the charged ion. If we can keep it charged, and we cannot keep it charged if the vacuum is not good enough. So what we get out of those a few thousand is just 60. We only can keep it for 60. We know it's longer. There is still something there, but we lose the ions. We cannot follow them anymore. So that's why it's just a threshold. If we improve our vacuum condition, and that's why we are setting up now a cryogenic Paul trap operating at 4 Kelvin, and this has been done for highly charged ions at many places, and they reach up to 30, 40 hours of storage time. So we have everything in-house now. We just received 2 days ago or 3 days ago the vacuum chamber. I think by the end of the year we have at least the setup working, and then we see how much we can learn to bring it into fruitful operation. So we have the technology to extend this lifetime measurement. And the microseconds, they come if you do the conversion, and then the conversion factor brings down by 9 order of magnitude the 10 to the 4 or 10 to the 3, depending, something like that, to the order of a few microseconds. And that's exactly what we measure.
And in this experiment, when you measured the energy of the electrons, why do you do this instead of measuring the energy of the photons emitted?
Because there is no photons. I spent 2 years of my life and wasted, no, I didn't waste, I shouldn't say that. Well, I wasted maybe money, but not the time of students, because they learned a lot. But we have a very nice, very expensive, very technologically challenging VOV detection system, which never saw a single photon, at least not from the nuclear decay. There is nothing. We cannot suppress internal conversion sufficiently to more than 9 orders of magnitude to see photons. That's why we have to take serious that at the moment we know that there is electrons coming out, and then better go the way, detect what you know that comes out, than search for ages what is not coming out like the rest of the world is doing it. It would be very provocative.
So the same reason for which you don't see 10 to the 4 seconds, but you see 60 seconds is the reason why you don't see UV photons.
No. The 60 seconds could be 10 to the 4 if we had a better vacuum. This would not change anything about the internal conversion or the photons. What comes there in the game is that we have the catcher surface. We have electrons which make the neutralization, which open up then this decay channel. And if we keep it contact-free in some storage area of a trap, then you would not have this internal conversion situation. You would stay charged, and then you would see again the photons.
I have still a question concerning the energy measurements. Can you go back one slide back? The final, the summary. This is the last point. No, this one, yeah. No, sorry. Okay, so you measure energy by electrons.
Yes.
With this bottled spectrometer. Yeah. But you also are planning to excite by laser.
Yes.
You can measure energy also in the second type, yeah? I mean, then you can narrow, this experiment where you take the coincidence with the electrons. So you shine the laser and you see the electrons coming out. In principle, by narrowing the laser band, you can also try to find where the isomer is. Or it will be not precise enough.
I hope we don't need that. I mean, we can go in steps of a few gigahertz or megahertz even, scan our laser over, let's say, 1 electron volt. And we made the exercise of calculating from the optical Bloch equations, everything from very basic points. We looked into what do we expect in terms of how many photons do we get out, how many excitations, assuming that we know what our source has as a density of the input of the target material. We get per laser shot about 4,000 excitations, and then we can calculate with lifetime what we will get out in terms of signal. 3 days are enough with a good more than 10 to 100 signal to background ratio to cover 1 electron volt of search range.
So 3 days per 1 electron volt.
3 days for 1 electron volt search range. Yeah.
Okay, so 3 weeks.
No.
And then you have.
You have to know where to search.
Yeah, but you go one by one. I mean, you can.
Yeah, but I'm sure we will barely need the 2nd electron volt.
Okay, so you believe that you will measure energy basically with this electrostatic method, yeah, like measuring energy of conventional electrons.
That is the goal, and from that we start our search range with a laser then. Of course, this is a good input then to start with. And we will probably start a little bit higher than 7.8 electron volts.
I have still another question concerning the CCD camera, because we are using also CCD camera and we love this technique. I mean, in these pictures where you show the bright dot in the middle, what is the exposure of the camera? Do you have amplification on the camera, or is just a long exposure accumulating?
No. This was a sampling of several hundreds of exposures of short time.
Okay.
And it's one of the camera that has the lowest dark current or dark count rate, about 0.05 dark counts per square millimeter and second. So this is really very low compared to what we expect as the rate from our decay.
So how quickly you see the dot? I mean, in the packet you have bunches, and one
Yes.
bunch is few hundred ions.
Yes, you see it.
Immediately on
You
the
see
one
it.
bunch you see.
You see it.
Okay. Fantastic. Any other questions? Yes.
You don't see single charged isotope.
I was waiting for this question.
Is it understood?
No, this is really, I call it in the meanwhile the thorium puzzle. As you may have noticed, I was only showing signals. We extract singly charged, doubly charged, triply charged. We only see, and what I was showing is doubly charged and triply charged. Not because I don't want to bore you with even more pictures, just we didn't and we don't see any signal from the single plus. And initially we thought, well, I've shown the numbers, our extraction in the single plus is an order of magnitude lower than the rest. It's maybe an efficiency issue. No. We checked that, we measured along, we were very careful in background subtraction. I can say we would have seen a signal if it would have been in singly plus available. So what does it mean? It can only mean that the de-excitation in the singly charged state is so fast and radiationless that it doesn't emit any electrons. So there could be some, let's say, now we come into a different regime of how people work with the thorium, the so-called electron bridge. Now we come in the nucleus atomic shell interaction regime. So there could be some resonant interaction between some transition in the shell and the de-excitation of the nucleus, which then makes an electron, a low energy electron, and a cascade of shake-off or Costa-Kronig or whatever type Auger electrons emitting, but very fast, such that we just don't see it. Actually, what we will do now is we want to make sure that this is not an effect of the 1 plus, which is just barely extracted, but that we can really reproduce it in a way that we will now quench an extracted 3 plus and an extracted 2 plus, which is together 15%, so our full efficiency, by putting selectively in some argon gas, and then making a charge exchange from 3 plus to 1 plus, from 2 plus to 1 plus, have it in the QMS identified, and then look if we don't see the signal or not. So we will now set up a search program to get better insight into the single plus. Yeah. But there is certainly something which is distinct from the 2 and 3 plus happening, probably involving some resonance states in the atomic shell.
Any other questions? There were many. So I think we thank Peter again.